Hello. In this video, we're going to look at another astable multivibrator or waveform generator. And in this case, it's a circuit that's going to produce both a square wave and a triangular wave. So I've referred to it as the square triangular waveform generator. And by looking at the circuit, you can tell that it consists of two stages. The first stage consists of a non-inverting Schmitt trigger, which will go all the way up to V1 here. And the second stage consists of an integrator with output V2. And so in essence, the circuit consists of a non-inverting Schmitt trigger followed by an integrator. Now we expect that the output of a non-inverting Schmitt trigger, or any Schmitt trigger for that matter, is going to be a square wave. And so the output is going to be switching between positive saturation and negative saturation. And therefore the output out of V1, we're expecting it's going to be a square waveform. And when we feed that square waveform into the integrator, what we're going to have is the integral of that. And so it's going to integrate when you have a positive value, when the output of V1 is sitting at positive Vsat. The integrator, because it's an inverting integrator, is going to have a negative slope. And when the output is sitting at a low voltage, or the low portion of the square waveform, then the output of the integrator is going to be a straight line with a positive slope. And so we're going to get out of V2 a triangular wave. So that's in essence qualitatively how the circuit works. Let's go ahead and analyze the circuit so that we can come up with expressions for both V1 and V2, our square wave and our triangular wave. We're interested in knowing what's going to be the amplitude of those waveforms, as well as the period of oscillation or the frequency of oscillation for the circuit. So I'm going to perform my analysis. And I'm going to draw my waveforms just so that we get a visual, as we go analyzing the circuit, we get a visual or a graphical understanding of what the equations are telling us. So this is going to be V1, which is the output of the Schmitt trigger. And so it's going to be a waveform which oscillates between positive Vsat and negative Vsat. Positive Vsat, negative Vsat, Vsat being the saturation voltage of the first op-amp. And the output of my integrator, V2, is going to be a triangular wave. And again, I'm expecting it's going to have a negative slope when my input to the integrator or V1 is positive, and a positive slope when the input is negative, because it's an inverting integrator. The signal V1 is being fed into the inverting input terminal of that second op-amp. But notice that the output of that integrator is being fed back to my non-inverting Schmitt trigger, and so it is what's going to cause my Schmitt trigger to switch between one state and the other. And the idea is that it's going to start at a certain value, that transition value, and then it's going to start decreasing again with a negative slope until it reaches that negative transition point, negative Vt, at which point it's going to cause the output of the Schmitt trigger to switch states, and so the Schmitt trigger will go low, and the output of the integrator is going to start increasing with a positive slope until it reaches that trip point again, that Vt point. It's going to cause the output of the Schmitt trigger to switch to high, and the cycle is just going to repeat itself. Now we know that for a non-inverting Schmitt trigger, the value of Vt, I'm going to write it here, my transition voltage is going to be equal to R1 divided by R2 times the saturation voltage of that first op amp. Let's just assume for simplicity that both op amps have the same saturation voltage Vsat. And so Vt is going to be proportional to the saturation voltage, but unless R1 and R2 are equal to each other, generally speaking, different from the saturation voltage. So that's what we're getting. Let's go ahead and perform the mathematical analysis now. And again, we're trying to find expressions for V1 as a function of time and V2 as a function of time, my square wave and my triangular wave. V1 is going to be fairly easy. V2, we need to figure out the relationship between Vt and Vsat. So let's assume a starting point, since we have assumed that my V1 starts at time equals 0 as sitting at the positive saturation voltage. We're going to assume that at t equals 0 plus, meaning right on the right side of the 0 axis, we know that V1 of 0 plus, or we're assuming that it's sitting at positive saturation. If that is the case, then, meaning assuming that this is switched to positive saturation, then V2 at 0 plus is going to be equal to positive Vt, which, as we have said, is going to be equal to R1 over R2 times Vsat. But for now, let's just work with Vt to keep things simple. We can do the substitutions later on. Because V2 is the result of integrating the signal V1, then I know that my V2 as a function of time, perhaps I can write that here somewhere. We know that in general V2 is going to be equal to, or phasor, V2 1 over j omega RC times V1. That's in the frequency domain. If we wanted to translate it into the time domain, we will have that V2 is going to be equal to negative 1 over RC times the integral of V1 of t dt. So division by j omega in the frequency domain is equivalent to integration over time in the time domain. So I'll have that this is equal to negative 1 over RC, integral from 0 to t of V1 of t dt. Now, since I'm integrating from 0 to t, I really should be saying V1 of tau d tau or some other constant of integration. But because tau is also the name that we give to the time constant, I'm going to avoid the usage of tau. So even though it's not very proper to have the same constant of integration as your limit, I'm just going to keep it as V1 of t dt. Plus V2 of 0 plus, meaning the initial value of V2. So I can now solve for that integral, replace V1 with its value, which is at this point positive Vsat times dt, plus, and my value for V2 is equal to Vt. Now if I integrate Vsat between 0 and t, Vsat is a constant, and so what I will get is basically Vsat comes out of the integral, and the integral of 1 times dt is just equal to t. So I will end up with V2 of t being equal to negative 1 over RC times Vsat times t. So I'll write Vsat on my numerator there. Plus Vt. And notice that this is what we are expecting to get. We're expecting to get a straight line, right? And this is a linear function of t, so it represents a straight line with a negative slope, the negative slope being negative Vsat divided by RC. plus some offset, because when t is equal to 0, we're starting at the value of vt. And so this is exactly what we are expecting, all the way from 0, or from 0 plus, to the half of the period, which I'm going to label as t1. So this point is going to be t1, that's t1 over here, and this is my period t, which is going to sit over here. Now, let's look at the value of the function from t1 to t. So, at t equals t1, I will have my v1 of t1, it's going to be equal to negative saturation, or if we wanted to be more proper, we could say, t1 plus. So, negative saturation, which means that v2 of t1 plus is going to be equal to now negative vt. So I can solve my integral again for v2 as a function of time, same thing, minus 1 over rc, integral from 0 to t of v1 of t dt, and v1 between t1 and the period t, capital T, is going to be equal to negative vsat, so negative vsat times dt, and my initial condition v2 of t1 plus now is going to be equal to negative vt, so minus vt. So we can see that v2 of t now is going to be equal to positive vsat over rc times t minus vt. So almost the complement of the previous function. So we can see again this matches our expectations from the graphical representation, where for t equal to t1, we will have that we will have a value of v2 equal to negative vt, and then it will go increasing in slope with a slope of vsat divided by rc. So if I wanted to put all of this together and just write down the equations, I will then represent my square waveform v1 of t is going to be equal to positive vsat between 0 plus and t1, we can call it t1 minus, and negative vsat between t1 plus and my period. And v2 as a function of time is going to be equal to negative vsat over rc times t plus vt for 0 plus less than or equal to t less than or equal to t1 minus, and positive vsat over rc times t minus vt between t1 minus and the period, or sorry, t1 plus and the period. So these are my mathematical expressions for those two waveforms. Again, we get a square waveform and a triangular waveform. A square waveform with amplitude plus minus vsat, triangular waveform with amplitude plus minus vt, which is going to be depending on vsat, and that proportionality constant is going to be the ratio of r1 to r2. So next we're going to take a look at the period of oscillation. How do we calculate the period or the frequency of oscillation, which note is going to be the same for the square wave and the triangular wave.